Hello students, welcome to the world of chemistry. This is Dr. Vikram Panchal and I am dealing with spectroscopy for chemistry. This is lecture number 31. In this lecture I will explain you solvent effect in carbonyl compounds, particularly pi to pi star transitions. In earlier lecture I have explained you n to pi star transition solvent effect. Okay, so here there is a pi state in carbonyl compound. There will be pi star state. In the beginning there are two electrons in pi orbital. Both are having opposite spin. When electron absorb UV visible radiations, one of these electron will transit to pi star state, but here because of the selection rule delta S will be 0 and therefore spin of this electron remain the same. But in this case, when electron transfer to pi star from pi BMO orbital, what happens? Let us see this. So when electron transit from pi orbital, that is BMO orbital, to pi star orbital, which is ABMO, we are increasing number of electrons in ABMO. So now the number of electron in ABMO increased. So in that case, bond order decreases. If you know molecular orbital theory, you must be knowing that bond order is equal to half BMO electron minus ABMO electron. So here, as number of ABMO electron increased, bond order also decreases. But if bond order decreases, then bond length increases. And of course, bond strength decreases. These are all effect of bond order. But if bond length increases, then that effect will appear on dipole moment. Then dipole moment, which is mu, equals to R into electric charge. Okay, and that if R increases, dipole moment also increases. Thus, polarity of pi star state increases. So in this case, pi star state of carbonyl group is more polar than pi state during pi to pi star transition. Now, here, when polar solvent is used for UV visible spectra, dipole-dipole interaction occur between polar compound, that is carbonyl, and polar solvent. As dipole-dipole interaction is stronger with more polar pi star state than pi state, the loss of energy of pi star state is greater than that of pi state. Therefore, pi star state is more stabilized than pi state. Therefore, pi star state is more stabilized and having less low energy than pi state. We will see this in the earlier figure here. This is pi star state and this one is pi state. Of course, there will be a change in both the states. So pi state will be reduced because of dipole-dipole interaction. And suppose a new state form, which is this one, it is a pi state having less energy, but this is little bit less reduction. But pi star state is more polar, which is having more dipole-dipole interaction with polar solvents, and therefore reduction of pi star state would be even more than that of pi state. So this is what happened here. So pi star state will be more stabilized than pi state, and here this is more reduction of energy of pi star state appear because of dipole-dipole interaction between these two molecules. And now when electron transit from pi to pi star, the energy difference is very less, and therefore delta E2 will be less, and therefore lambda 2 increases. This is a pi to pi star transition, but in presence of polar solvent. And here we can see that delta E2 is less than delta E1, and therefore lambda 2 will be greater than lambda 1, and this makes the lambda maxima shift towards more wavelength, and therefore lambda maxima increases. This is called red shift. Okay, so when we observe the effect of a polar solvent on carbonyl compound, the pi to pi star transition will shift towards higher wavelength because of the presence of polar solvent. So this is the reason what happened here, and therefore we can say that the energy required for pi to pi star transition is comparatively less. low. Therefore, delta E2 will be less than delta E1. So we can say that lambda 2 will be greater than lambda 1 because both are inversely proportional. And in this case, lambda maxima will shift towards higher wavelength, which is called bathochromic shift or red shift. So this way red shift appear in pi to pi star transition and blue shift appear in n to pi star transitions. We can take one example to understand both these cases, and let us take mesitile oxide, because mesitile oxide is a perfect enone system having both carbonyl group and C double bond C group also. So see the effect of solvent on lambda maxima, epsilon maxima for pi to pi star transition, as well as lambda maxima, epsilon maxima for n to pi star transition. So when solvent is normal hexane, then lambda maxima will be for pi to pi star transition 230 and epsilon will be 12,600. For n to pi star it is 327 and epsilon maxima is 98. But in case of ether is also non-polar solvent. This lambda maxima remain the same, 12,006, epsilon also same. Here it is almost same, 326 with epsilon maxima. But if you use ethanol is a polar solvent, and therefore you will find some change over here. 237 with 12,600 epsilon maxima. Here it is 315 blue shift. See the value of lambda maxima decrease with decrease in intensity also. If you use water H2O, then it is 245 because it is more polar, and epsilon maxima value also decreased 10,000, and here it is 305, again decreases. Blue shift, this is red shift, and here it is blue shift with low intensity. So this is the effect of solvent on carbonyl compound, okay, pi to pi star transition as well as n to pi star transition. So that's it in this lecture. Thank you so much.